second webinar on Sidestream series, Nitrogen Removal Case Studies. Today our webinar will go from noon to 1:30, and the workshop continues our series on Sidestream treatment with case study overviews of two different nitrogen ammonia Sidestream removal technologies. Today we're very fortunate to have two presentations. In the first presentation, Steve Walker and John Fraser of Carollo Engineers will present an overview of the installation of centrate and RAS reaeration basins, CARB, to treat the nitrogen-rich centrate from dewatering at the Robert W. Height Treatment Facility in Denver, Colorado. In the second presentation, Dr. Henrik Meltzer of Brown and Caldwell will present an overview of the Demon pilot system operated at the Chambers Creek Regional Wastewater Treatment Plant in Pierce County. This pilot was one of the first and largest pilot studies to evaluate an anaerobic ammonium oxidation, ANAMOX, technology in the United States. Each presentation will last approximately 35 to 40 minutes. Afterwards, we will have about a 5-minute question and answer session. I'd ask that you please hold your questions till the end of each presentation, and if you look at your viewing pane in the bottom, there's a pane for typing in questions, and we'll take as many questions as we can in that about 5-minute period before we start the second presentation. I'd certainly like to thank Steve Walker, John Fraser, and Dr. Henrik Meltzer for taking the time today for sharing their knowledge with us. I'd also like to thank Rick Kelly of Brown and Caldwell, the chair of the Emerging Technologies Committee, and the other members for organizing this series of webinars for us, and Michael Rainey from PNCWA. So with that, let's start our first presentation. The title is Sidestream Treatment Process, Centrate and RAS Reaeration Basins. Michael, are you going to switch this over to Steve?
Yes.
There you go. So for our introduction, Steve Walker has over 30 years of experience in wastewater treatment. He is the Operations Assistant Group Lead for Carollo Engineers. Prior to working for Carollo, Steve was the Treatment Superintendent for the Metro Wastewater Reclamation District in Denver, Colorado. He's a licensed wastewater operator in Colorado, California, and New Mexico, and serves on the State of Colorado's Water and Wastewater Facility Operations Certification Board. Steve holds a BS degree in Technical and Industrial Administration from Metro State College and an AAS degree in Water Quality Management from Red Rocks Community College. In 2005, the Rocky Mountain WEA Joint Technical Activities Committee awarded Steve the William J. Hatfield Award for Outstanding Performance and Professionalism in the operation of a wastewater treatment facility. His co-presenter today is John Fraser, a Senior Vice President and Wastewater Practice Director with Carollo Engineers, specializing in the planning, design, and startup of medium and large-sized wastewater treatment facilities. Mr. Fraser is a leader of Carollo's National Nutrient Reduction Services team and has been involved in Sidestream treatment evaluation and design at several facilities across the U.S. Mr. Fraser served as a project manager for both Denver Metro's $50 million North Secondary Improvements Project and $150 million South Secondary Improvements projects at the Robert W. Height Treatment Facility. Both projects included bioaugmentation Sidestream reactors in a unique CARB configuration.
With that, it sounds like we're off. Hi, everybody there in the Northwest. I'm Steve Walker, and this other voice next to me is going to be John Fraser. We're in the Denver, Colorado area today, but feel very fortunate to speak with you up there. I will just preface, I'm struggling through a migraine today, so if it sounds like I drop off the end of the world, there's a reason for that. And John knows enough to pick up when I struggle. So off we go. For some reason it doesn't, there we go. Just to set this up at the beginning, there's a reduction in nutrient standards is happening throughout the United States. We've seen it where we're ratcheting down our ammonia, and then we've gotten into where they're starting to focus on total nitrogen, which is ammonia nitrate and nitrite, and everybody's effluent. This is from Maine to Florida and from Southern California to the Puget Sound. On top of that, the regulators are now also focusing on total phosphorus. Both of these reductions seem to happen in the same type of secondary treatment processes. So we actually have competing treatments happening basically in the same footprint. Go ahead, John. All right. And then at the same time, I'm an operator, John's an engineer. The wastewater agencies are being asked to do more with less. As an operator, we're trying to get more work out of the existing facilities, the existing personnel, the existing budgets. And the engineers are being asked to implement the most cost-effective solution. So how can we go about removing this ammonia and nitrogen products and removing the phosphorus without driving up our ratepayers' budgets or our ratepayers' costs? Go ahead, John. Please take this slide.
So I think what Steve's pointed out in this slide, and you're probably mostly familiar with, is there's several recycle streams that tend to bring high loads of ammonia back to the treatment process. And so the whole concept of side stream treatment that the industry is looking at is related to, what if we took these side streams and treated them separately? Is there any advantage in a cost profile and a performance profile for handling side streams separately? So some of the challenges associated with these streams, of course, there's streams that come off thickening, and there's streams that come off of dewatering, particularly dewatering after solid stabilization in an anaerobic condition. And these have several impacts. In the digesters, for example, the release of nutrients that get returned through recycle streams from dewatering is pretty much proportional to the VSS destruction. So as volatile salts are destroyed, they release their cell material, and that cell material contains a lot of nitrogen and phosphorus. Turns out when you look at these side streams as a proportion of the load to the plant, including the inflow load and the side stream load, they're pretty significant. It can be on the order of magnitude 10 to 30% in the nitrogen component. And in fact, those plants that have consolidated solids handling from multiple facilities tend to have a much higher load. And this Denver example is one that had about 40% of the nitrogen load coming back from dewatering recycle streams, because it handled biosolids from two separate plants. And the phosphorus is the same story. A significant part of the phosphorus load comes right back around after dewatering. So we know that there's a target there, a target opportunity. So let's take a look at what what side stream treatment might be able to do for you.
We've got some, there's different ways to go about tackling nutrient management. We can export our problems to somebody else with regional facilities or to facilities that have less stringent limits. These are likely not long-term feasible. We can figure out how to manage these problems with operational modifications through equalization or through mainstream treatment modifications, or we can look at treating it through some sort of either biological or physical chemical treatment. And for us today, we would look at what would be the difference between doing the mainstream modifications and or doing this either managing the problem or treating the problem. Alrighty. So for today, we're looking at side stream treatment, and this we're going to start focusing in on exactly what was experienced at the Denver Metro plant and then how that can be applied elsewhere. The side stream treatment does provide some cost-effective nutrient reduction. Why would we even entertain side stream treatment? primarily it's a low flow. You're just treating a small portion of that total flow that's in any treatment plant. And that's a high strength flow, so we've got a better idea of what kind of load that we're dealing with in that small flow. We can use a selected biomass. You'll find out as we talk further today that we can actually grow the nitrifiers in a little nitrifier type environment to go after the ammonia in a localized environment. We can use existing features if they're there. For instance, if you've got an extra tankage, an extra primary clarifier or two, or you've got some aeration basins that have been taken out of service for some reason. And there's probably, we can do this without modifying the mainstream treatment processes within the treatment plant. In this particular example, this is exactly what happened at Denver Metro. In 2001, we went through a master plan study to look at what was the best approach to deal with the ammonia load that was being generated at that treatment plant and that ammonia load that was arriving at that treatment plant. Just in round figures, the ammonia load that was coming into the treatment plant was about 60% of the total ammonia load on the plant, which meant the centrate from dewatering was 40%. Those numbers were actually 8 to 10 tons per day coming into the plant and 6 to 8 tons per day coming out of centrate treatment on bad days. So we had to figure out a way to do this cost effectively. Throughout the master plan, we focused in on building additional aeration basins and with additional clarifiers to handle that load in a traditional manner. As we got into that, we determined that was going to cost, and this was in roughly 2001 dollars, $38 million to build 18 million gallons of capacity. Big numbers. This was a big plant. It was that particular time it was 167 million gallon a day footprint. So as people got to putting their heads together and thinking about different ways to go about it, we went over to New York City, who had been experimenting with centrate treatment, and learned about different ways to handle centrate and how you could reduce that ammonia load on a treatment plant. Came up with a design at Denver Metro that resulted in a Sidestream treatment system, which was roughly $21 million to get what turned into at least 22 million gallons a day of treatment capacity. So tremendous savings, and it's literally we got equal capacity increase for about 50% of the capital cost. So we met that ideal of trying to provide the ratepayer the best possible cost we could and still get the treatment goals that were desired. Right ahead, John. I need to read.
So want to explain a little bit about the CARB system in Denver. We've shown a schematic illustration of the basic elements of a MLE BNR process for nitrification and denitrification, with an aerobic zone for nitrification and mixed liquor recycle to the anoxic zone for denite. And in a case where the centrate flow is all blended at the head of this process with the primary effluent and essentially treated through the MLE process. The CARB system puts a parallel aeration basin into the system and brings RAS from the final clarifiers back through the CARB basins as a seed for the nitrifiers. And then instead of introducing the centrate flow with the rest of the primary effluent, that centrate flow is routed back through the CARB basin only. So what we have is a system that has a seed of nitrifiers coming from the mainstream and then being fed a substrate of high ammonia that comes back in the centrate return. So we set up an environment of high ammonia that facilitates the growth of nitrifiers in this Sidestream reactor. We call it CARB in case anyone wonders, because the tidal, centrate, and reaeration basins didn't fit on the tidal block of the drawing, so we had to shorten it up And if you ever hear this term, that's simply what it means, centrate and RAS reaeration basins. Pretty much calling the name that it is. So we've also shown here a schematic that's more BioWin type output looking for those who enjoy process simulation modeling that essentially shows the same system of a multi-stage MLE process with some aerobic and some anoxic zones, a RAS return coming off the clarifiers, and then a portion of that being routed through a carb basin for side stream treatment with centrate being fed into the carb basin. Typically what we designed around in this case is about 1/3 of the RAS flow going through the carb basins and about 2/3 of the RAS flow bypassing the carb basins. And actually Metro's done some testing on this number, and they can manipulate the environmental conditions and get different performance outcomes by varying the amount of RAS that they put through the side stream treatment. So if you think about this, and you have a typical activated sludge that's running at maybe 2,500 to 3,000 milligram per liter of mixed liquor in the aeration basins, that goes through a secondary clarifier, and there's a compression factor on the RAS. And let's say it's 2 to 3 to 1. I think we've shown 2.5 to 1 here. That puts a mixed liquor concentration of about 6,000 milligram per liter into the side stream treatment basins. And that's really important concept of the side stream treatment, because now you have a system that's operating at a high mixed liquor. The SRT and the footprint can be dramatically reduced in the side stream basin. And that's part of the reason that it's so cost effective compared to doing the job in the mainstream treatment process. So what's happening in the side stream treatment carb basin? We're reducing ammonia load that gets returned back to the aeration basin, but we're also improving the nitrification, denitrification stability, because that side stream load kind of gets dampened out in a large buffer that's in the carb basins, and the stability of the overall process improves dramatically.
Some of the features that distinguish carb from some of the other treatment processes that are out there. With this carb process, and here shortly, for those of you that are getting confused, you'll see an overview, and some of this will start coming together for those of us that like to see aerials with concrete and arrows on it, but instead of BioWin models. We get a continuous seed of mainstream nitrifiers. From that carb basin, it's constantly being fed 24/7 RAS flow, and it's constantly being, or it's consistently fed centrate. So anytime there's flow coming into that basin, there's flow going out, and that flow goes back into the influent, back through the aeration basin. So there's nitrifiers consistently going to every aeration basin that's being fed, that's in service that particular day. There's flow going through the reactor. It's not a sequence batch reactor type of process as some of the other different types of ammonia reduction processes are out there. From an operator, I'm not a batch type of person. I like to be able to operate something continuously, turn it on and off when I want to, not wait for it to run through a cycle. It's suspended growth. There's no media. There's not an IFAS type media with certain nitrifiers growing on it to do this kind of work, as is seen in
well, similar to an Etamox, you know, I know Dr. Meltzer talking about Demon and Anamox processes. There's one of those processes called an Etamox that is essentially an Anamox with IFAS media. This particular process doesn't rely on any suspended growth on IFAS media.
So it's a different kind of maintenance requirement for a suspended growth than it is for the carb type basin. There's no secondary clarifier, and there's no additional RAS required. There's no temperature control. The Sharon process, we know, requires temperature to maintain the ammonia reduction. This one, there is no temperature required to maintain the carb process. It does provide bio-augmentation of the mainstream process. What that basically means is there's a whole group of microorganisms ready to do denitrification flowing into these aeration basins, flowing into those anoxic zones, ready to go to work. These guys are on steroids. They're jazzed up and ready to rock and roll. And there's denitrification happening in the mainstream, something we discovered over time, and John will elaborate a little bit more in detail, but there's some additional treatment happening within the different channels and flow streams on the treatment plant. This is what the actual plant looks like. You'll notice there's these carb basins are over here on the left-hand left-hand side of the screen. There are 4 of them, carb basins 1 through 4. When this treatment plant was originally designed in 1965, Mead and Mount were the designers. They are no longer in business as far as I know. But this particular area where these carb basins were set was left open, and for years we used to play basketball right here and have picnic tables. But it was set up for some sort of pre-aeration of secondary treatment by the designers in 1965. Well, that area became available, and as we got into the master planning and then the planning for this particular project, it became apparent that this was an ideal spot to put this particular material. The benefits of our carb process, just to drive them home again, we partially nitrify the centrate. On the next slide we'll show you where it comes from. We generate nitrate for denitrification, in the MLE basins. It provides the same function as internal mixed liquor. We inventory MLS at a higher concentration. The bugs inside of the carb are 6,000 milligrams per liter. The mixed liquor inside of the aeration basins are roughly 2,000 to 2,500 milligrams per liter. That reduces the load on the secondary clarifiers. That was of tremendous importance in this particular treatment plant. The existing clarifiers, there's 12 of them, have 10-foot sidewalls. And as part of this upgrade, those sidewalls remain 12 feet. It's a very expensive undertaking to dig those deeper. The decision was made to leave the clarifier sidewall depth alone. The internals were modified, but the sidewall depth remained the same. We buy out, once again, we put these nitrifiers into that mainstream, which gives us a boost in treatment. This is what the plant looks like. The PE comes right down the main channel here. Centrate is brought from it's roughly 1 million pounds a day worth of centrate going into 1 of 4 carb basins. Each one can be fed equally or in any proportion thereof. And over time, the district has been experimenting, and right now I believe they're running 2 basins in a carb process, and they're experimenting with 2 other ones in some other modified form of ammonia removal as they play with their processes. Once again, the P goes right down the middle, and in the original old plant, these were 4 distinct quads. There was 3 clarifiers and 3 basins connected to 1 RAS pumping station. For me as an operator, I had 4 distinct treatment plants I had to operate out here. It was a pain in the you-know-what, trying to figure out which one was operating as what. And with a rectangular channel with basin, square rectangular gates coming off the side, loading into each one of those basins was never quite the same. So between the you could go from one basin to the next one side by side, and there would be a 400 to 600 milligram per liter difference in the density, the concentration of the material inside of those basins. It was driven just by the way the main channel fed these basins. As part of this upgrade, that feeding problem was eliminated. The RAS originally came back from the clarifiers into one of these 3 basins. The clarifiers did not withdraw consistently, and then we always had a blanket on the furthest one away where you wouldn't have a blanket on the nearest one. Once again, you'd have problems with solids blowout out of one of the clarifiers. That was modified as part of this project. But the important thing to note here is this RAS is now back, and it's introduced into the carb basins. It is also introduced right between the carb basins back to the main channel, as demonstrated by that arrow there. So roughly up to 70% a day of the RAS goes right past carb right back into the main channel, mixes with the PE effluent, and goes into the aeration basins. What this provided was a common influent to every one of those aeration basins, and I'll demonstrate in the slide coming up here. We had common mixed liquor concentrations throughout almost immediately after starting this process up. Go ahead, Don.
So the district incorporated this carb process for Sidestream treatment into their north secondary modifications, and early results were successful for them. So they elected to incorporate the same process into their new south secondary plant. This plant just went online the first of this year when the new discharge criteria for the river went into effect. And this is a 114 MGD MLE DNR facility that was essentially on a greenfield spot within the plant site. And let me just really quickly show how carb was incorporated into their south secondary plant. This is an example of we had a clean slate to put carb wherever it made the most sense performance-wise and hydraulically and technically. We're kind of in where it put on the north plant. We have a free piece of paper on the south plant. So there's a primary effluent pump station that splits primary effluent between 6 parallel aeration basins. RAS is returned back to the head of each of those aeration basins, mixed with PE, and goes to a single pass aeration basin. A portion of the RAS is also brought back to 3 carb basins that are located kind of on the opposite mirror image side of the 6 aeration basins. And then centrate is also fed into those carb basins, and then the effluent from carb is mixed with the mixed liquor return and flows back through some channels to the anoxic zones of each of the aeration basins. So this was a little bit more ideal piping and hydraulic orientation in this facility than it was when we didn't have a clean slate to work with. So Steve, why don't you talk about the overall end result?
With the original master plan, with the permit criteria at Denver Metro, we were allowed something to the effect of up to 15 milligrams per liter of ammonia, and with also nitrate was well above some number like 7 or 8 milligrams per liter on a monthly basis in the early 2000s. Over time, first thing that was tackled was the north secondary with the carb modifications. That plant went up to 106 million gallon a day capacity. The south plant, which doesn't show the full transition here, was a Purox system, treated roughly 60 million gallons a day on a good day with no ammonia reduction. So you had whatever 30 milligrams per liter of ammonia coming in, that's what went out the other end. Over time, with all the modifications with the new permit, we are now being required to produce ammonia under 2 milligrams per liter at all times, and we have a weekly nitrate plus nitrite value of under 8 milligrams per liter as a weekly for both the north and the south. These two effluents are blended to make the final effluent number. As you'll note here in the center, there is roughly 1 million gallons of centrate being produced daily. When the plant first started up, the north secondary was being fed that total ammonia load at roughly 1,000 to 1,200 milligrams per liter of ammonia going mainlined right into this whole process here. Since the startup of the south, that load is now being split roughly 50-50. There's some additional design features that went into carb that help us operators. There's some swing zones that are designed in there for DO suppression and future denitrification. Those are outlined here. You'll notice that we have fine bubble diffusers and just a mixer depending on which mode you're going to run that swing zone in. There's alkalinity and carbon addition. You need alkalinity for nitrification potentially, and the district has, the Denver Metro District has had some issues with pH control, so over the years, and alkalinity was determined that it may be something that was needed. I don't believe it's been used since this process has been started up. And then carbon feed to ensure denitrification is happening. You've got enough carbon to make sure that that process kicks.
And that denitrification in the carb basins was intended for future phosphorus reduction. So if the plant went to future phosphorus, they would have to denitrify before they went into the anaerobic zones. That's not being used right now because they're meeting their phosphorus in other ways, but that was designed into the facility to allow phosphorus removal in a carb system as well.
Right on. One of the other features of carb is surface wasting. You'll notice this is a rotating weir, not unlike what you see on some clarifiers. It's built into the end of the carb basin. What it allows us to do is capture that floating scum that comes out of that carb basin footprint and waste it off of the treatment plant. On this particular plant, it goes to a dissolved air flotation process. Since the carb is aerated, the filaments want to float. They'll float up and be wasted off. Since the RAS is returned back 30 to 40%, whatever the set point is of RAS, total RAS in the plant is going through this carb basin over a period of time. In theoretically within a day, any of that RAS is going to go through a carb basin. A good portion of those filaments are going to float up and be wasted out. Therefore, that filament problem, and folks that know the Denver Metro plant knows back in the late 90s, you could walk across some of these aeration basins and not sink. That particular problem is no longer an issue at the Metro District whatsoever.
Yeah, I think the point on that surface wasting, Steve, if you go back one slide, is it's a great feature if you guys can incorporate it anywhere into your treatment facility. I know that BNC and Denny Parker are big advocates of selectors, and the configuration may be a little different, but the philosophy is the same, that if you have a spot where all the RAS passes through, that you can surface waste off of that. It really helps the process perform better, and carb or any side stream process might offer that opportunity for you, and you should think about taking advantage of it.
All righty. So there was, we'll go into how this thing is performed, and then pretty soon turn it over to Henrik. With the startup, we evaluated the carb system and then assessed the overall activated sludge performance, and we did some refining, and then we'll talk a little bit about some future carb possibilities. When we first started this thing up, within a week, literally within a couple of days, we determined we were getting 85% ammonia removal in the carb basin. Good portion of that ammonia removal was happening within the first 100 feet of that basin, well before we thought it was going to happen. The design goal for the entire basin was 50% reduction. We were getting 85% reduction, literally into the middle of the first aerated zone.
And just to note, for those of you considering this side stream treatment, so often what limits the performance of the side stream is alkalinity limitations. So you're alkalinity limited, and you can only get so far. That's what the models predicted. We would only get 50% removal due to alkalinity limitations. It turns out that RAS is a good source of alkalinity, so we were able to run a little higher RAS rate through carb and drive more nitrification in the side stream and avoid some of those alkalinity limitations. And you look at the nitrate profile, and it just pretty much mirror imaged and what we anticipated for the ammonia reduction. And so we got much more nitrate because we had more ammonia removal produced in carb, and what that just resulted in is great denitrification when we got to the anoxic zones in this process. This is a chart that kind of shows the before and after startup of CARB for the entire north secondary. This shows the effluent nitrate and ammonia concentrations, and then the sampling day. This period here was before CARB started up, and this period was after CARB started up. We also showed with the X's the ammonia, and I wanted to show you that the ammonia coming out of the overall plant wasn't impacted. It was running about 1 to 2 milligram per liter before CARB, running a little bit higher, but about 1 to 2 milligram per liter, certainly below discharge criteria after CARB went online. But the big impact was the overall impact on nitrate reduction. So we were creating so much nitrogen that we dropped from 13 to 15 milligram per liter before CARB. We were creating so much that nitrate, that we were able to remove that in the anoxic zone and drop down to 7 to 8 milligram per liter. Currently, both the north and south secondary are operating at close to 5 to 6 milligram per liter of nitrate after a couple years of being able to dial this process in. A couple things on bioaugmentation. You know, I wish I could show you some scientific data that can quantify the impact of bioaugmentation on the process. I don't have that. I think the industry's working on that. We're certainly working on that. But I'll give you some anecdotal information that the winter time 16 degrees C SRT for this facility was designed at 4.2 days. That's the aerobic SRT. The operators at Metro intentionally reduced the SRT during the winter to see what the process could do, and were able to bring it down to 3.5 days before they had ammonia breakthrough. And if we can assume that that reduction between design SRT and actual operating SRT is partially attributed to bioaugmentation, it's about a 17% reduction in wintertime SRT, or a 17% benefit related to bioaugmentation. So I'm a personal believer in bioaugmentation. I think the challenge for the industry is to quantify the amount so that the design engineers can start incorporating that into the design process and saving money for the operators of these facilities. So a couple lessons that were learned over the first 5 years of operation is that this CARB process was pretty sensitive to pH due to rapid nitrification. This quick drop that was unanticipated in ammonia ended up resulting in a drop in pH in the later zones of the process. So what the district did is they added online pH probes and then tied those probes to the operation of the facility. And what they do is they increase the RAS rate if the pH gets too low, which essentially drives the profile more toward the end of the basin, and they control the degree of nitrification throughout the basin. The other tool that they use is they change the number of CARB basins that are online. They found that they can operate pretty well with 2 CARB basins rather than 4 with the loads that are going to that north side without causing pH drops. So where the facility was originally designed for about 20% of the total biomass in CARB, subsequent work has shown that really you only need about 10% of the inventory to get that nitrification that's anticipated and limited by the amount of alkalinity that you have. Here's a little bit longer term performance.
We've got about 2 minutes left.
Okay, we'll wrap up. Some longer term performance shows that, you know, they run in the winter time at maybe 60% removal up to 90% removal. And so the district really likes to run this facility in 45 to 60% range, and they do that by varying the number of basins online because they've got enough plant that they don't need to push that any harder. So real quick, I'd like to share something that the district has done recently. They noticed something interesting during startup, that the nitrogen balance was not preserved. So what came into CARB basin in the form of ammonia and nitrate was not preserved through the process. they were measuring an apparent loss of about 23% of TIN. So the question is, where is that TIN going? Possibly, are they having nitration, simultaneous denite, some other thing going on in those aeration basins? So they purposely set up the carb to test that. What if we tried to drive nitration? Can we get better performance out of the side stream? And so what they did is they played with increasing the centrate to RAS ratio, and that increased the temperature, created some more free ammonia, and increased the HRT. They also modified the aeration pattern to have aerobic, anoxic, aerobic, anoxic, and create some transient anoxia. And both of those actions, repressed NOBs and favored AOB formations for nitrification. So the results of that work showed that if they controlled this, they could get up to 51% total nitrogen reduction in the side stream, where they observed 23% without doing anything, 51% if they tried real hard, and they found that they could be stable at about 40 to 45% TIN reduction. So that was a great lesson for them, that if they wanted to even do better with some nitritation in carb, it was possible to do that. Steve?
All right, so we're wrapping up now. We got 2 more slides, folks. Oh, excuse me. What were the operational lessons learned from? We learned that RAS is crucial for optimum performance. It truly is. There's a lot of alkalinity. Whatever alkalinity is going out in the effluent of your treatment plant, whatever goes out in your clarifier effluent is also in your RAS. So if you've got 3,000 parts of alkalinity, or I'm sorry, 300 parts of alkalinity going out in your effluent, that can also be returned in your RAS. You need that RAS to support nitrification. You need that alkalinity. It allowed operation of the mainstream process to lower that mixed liquor concentration, which lowered that solids loading on the final clarifiers. For me, that was important as we went through construction, because 3 of these clarifiers were offline at any given time. But afterwards, with the 10-foot sidewalls, it still allows us to operate this plant with an awful lot of flexibility. The basins can be isolated to preserve biomass through storm events. If you can picture this, if you know you've got a storm event coming, we all watch weather, we can shut off a portion of that RAS that's going to these basins, keep the centrate coming in if we want. We're storing all those solids at 6,000 to 8,000 milligrams per liter in these basins. After the storm event has passed, we can release these solids back into the basins. These bugs are ready to go back to work, and we haven't lost them to the effluent like sometimes happens in a treatment plant. We've reduced the filament concerns, and then we've improved flexibility for different kinds of maintenance events.
So in conclusion, we found that carb provided successful nitrification of that side stream, and that it was at a lower cost than conventional treatment. Got it up to 85% ammonia reduction, but it can be pH sensitive, and there are ways to improve the stability by managing the nitrification in the side stream. And also, finally, that if desired, carbs can support nitrification as the processes of side stream treatment evolve and grow in the industry.
And that's what we have for you today. Thank you, Jen.
Thank you. I think we have time for perhaps one question. So what do we have here? What is the oxygen uptake rate in the carb basin, and what alpha factor is assumed?
That's an interesting question. I don't have the number off the top of my head. Now I have to go get that and let you know. Related to the alpha, couple things. You might have noticed that we have a full floor coverage aeration in the carb basin. So there's diffusers packed as tight as we can pack those, because we felt it was going to have both a lower alpha, like we see in other processes that operate, in the 6,000 milligram per liter range, and so we wanted to compensate that. And we also felt it was highly aerobic, and we needed to really jam a lot of air in the side stream process. So I think you can anticipate and design around a lower alpha. I don't know what value we used. I'd have to look that up, but we did account for that. But it turns out that the Metro District, they're pretty creative, and they don't like to spend money on aeration if they don't have to. So they turn the residual oxygen set points way down. So where we had started out recommending maybe 3 milligram per liter, maybe as low as 2, they're operating closer to 1 milligram per liter and getting great performance out of that. So it turns out that the alpha factor impact and the number of diffusers wasn't as significant as we thought.
Okay. Well, thank you very much. If we have time, we can take additional questions on the CARB process at the end, but it's time right now to switch over to Dr. Henrik Meltzer. Michael, do you want to change the presenter? So our second presentation of the day is pilot scale testing of Demon Sidestream treatment for expansion of Chambers Creek wastewater treatment plant in Pierce County. And our presenter is Dr. Henrik Meltzer. Dr. Meltzer is a wastewater treatment process engineer with Brown & Caldwell with more than 30 years of experience. He is the company's senior process lead for the Northwest Business Unit for biological treatment plant design. His work is focused on process modeling of biological treatment systems with and without nutrient removal, the design of aeration systems, and plant capacity assessment through the use of computer simulation tools and stress testing of clarifiers and solids handling equipment. His specific design experience includes conventional activated sludge, membrane bioreactors, sequencing batch reactors, oxidation ditches, nitrification, denitrification, biological phosphorus removal, trickling filtration, chemically enhanced high-rate clarifiers, and Sidestream treatment processes. Dr. Meltzer also oversaw the first ever Animox Sidestream pilot study conducted in the Pacific Northwest at Chambers Creek Wastewater Treatment Plant in Pierce County, Washington. Heinrich.
Good afternoon, everyone. I'm pleased to be able to present this material on behalf of the Chambers Creek Wastewater Treatment Plant staff and my colleagues from Brown & Caldwell that participated in this pilot test. Just a quick outline of what I'm going to cover. I'll begin with a short background of what led us to the pilot study, a little bit about the Animox technology, and then I'm going to focus mainly on the pilot study and finish off with some design criteria for the system that's under construction right now. So the Chambers Creek facility, the design was based on a growth-driven expansion, as you can see, from 29 to 45 MTD on a max month basis for the year 2030. Currently, they're really only regulated for BOD and suspended solids removal, and there are no nitrogen removal requirements for this plant. But folks in the Puget Sound area are all anticipating some form of nitrogen limitation. And given the fact that we had to expand this plant, we designed it in such a manner that we could modify the operation such that we could meet the 3 levels of discharge criteria shown on the screen for the different seasons, summer, winter, and then something we call shoulder, which is related to runoff and snowmelt conditions. The plant then is built to be very flexible, so it can satisfy any of these 3 sets of criteria. Incorporating Sidestream treatment seemed to offer significant cost advantages because, as Steve mentioned earlier on, the dewatered sludge dewatering stream is relatively low flow compared to the total plant influent, and about 20 to 30% of the influent ammonia load is associated with this stream. It's also, in many cases, delivered on a non-continuous basis. It's a function of when the plant chooses to operate the dewatering equipment, and it's also very hot. Dr. Stenzel presented on the same topic, Sidestream treatment, a month and a half ago or so, and I just want to recap in one slide the essence of the Anamox technology. Anamox then is short form for anaerobic ammonium oxidation, and what it allows is for two-thirds, or for a large part of the typical nitrification, denitrification one is used to seeing in biological nutrient removal processes, as was described in the previous presentation. We, in this case, allow for partial nitrification to nitrite nitrogen here using the AOBs, and that process is stopped, at which point the Anamox bacteria take over and grab a mole of ammonia and a mole of nitrite and go straight to nitrogen gas in a one-step biochemical process. And the NOBs, the nitrite oxidizing bacteria, are inhibited through the control of dissolved oxygen and the pH and in some cases temperature. So all of this is essentially eliminated, and the costs associated with running these parts of the nitrifying, denitrifying process are eliminated. So these are the this is really what we're taking advantage of in this Sidestream treatment approach. At the time that this was being considered, the only commercially available Sidestream treatment process using Anamox bacteria was that offered by the Demon technology, which is available in the United States, and it takes advantage of the granular structure of the organisms. You can see here these tiny, tiny pellets. I like to think of these equivalent, at least you would recognize the size and shape if you think of chocolate sprinkles on ice cream. That's what they look like and feel like. So because they're very dense, they settle very well. The SVI is typically much less than 50 mil per gram, this should read. And this allows us to take advantage of the sequencing batch reactor technology. And there is some control to minimize the growth of competing organisms, as I was inferring the NOBs. And there are controls in place to exercise or manage the pH to around 7 and the dissolved oxygen on the order of 0.3 milligrams per liter. There are two patents associated with this technology. One is associated with the pH control system, and the other one is the use of hydrocyclones, which seem pretty simple technology, but until people stumbled upon this, it was this process was a little unstable. But the use of the hydrocyclone takes advantage of the density difference between these granulated or granular organisms and the other offending organisms that we really don't want in there, like the heterotrophic denitrifying organisms. And they are literally spun out of the mixed liquor. The enriched mixed liquor is then returned to the process, and the offending or unwanted other organisms and then discharged from the process. That simple invention allows for a really optimum set of conditions to be developed for this type of technology. Just a few more details about the Demon technology. Typical loading rate is shown here, and the typical ammonia and total nitrogen removals are on the order of 85–90%. It's a relatively low energy demand process. Shown on the right-hand side is an extract from the WRF report on energy self-sufficient plants, and it shows the information from the Strass Austrian plant, which is the first plant where this was demonstrated, and the chart here illustrates the point at which, when they added the Demon process, in addition to other changes that they made in the plant, they were able to achieve a certain degree of self-sufficiency in terms of not being reliant on external power. They were able to maintain full operation without, and then save a lot of operating dollars. The process is sensitive to nitrite accumulation, and we'll speak about that later on. And there are almost 48 plants which have been in operation for 8 to 9 years now, as of 2013. In this country, or in North America, there's one in operation at HRSD in Virginia, another one that I understand is in operation in Florida. The ones in design are in at DC Water to service the condensate from the newly constructed Canby process. That's pretty close to startup, and another one that's close to startup, if it's not already started up, in Guelph, Ontario in Canada, and then obviously Pierce County's plant. So let's take a quick look at what convinced Pierce County to take a look at this technology in more detail. The role in this case, if you do the math, the Sidestream treatment process was required to remove between 1,500 to 2,000 pounds of nitrogen per day. And looking at it from the 10,000-foot overview, we estimated there would be a $400,000 per year in savings in operating costs, primarily as a result of the 600 to 700 gallons per day of methanol saved as a result of eliminating denitrification for the Sidestream, and the 2,000 SCFM on a continuous basis because of the oxygen that was saved and not having to go to full nitrification. If you look at the operating costs on an annualized basis, for each of the 4 modes that we could operate the plant, that is in a non-nitrifying mode, and nitrification, with no nitrogen removal, and then nitrogen removal with Sidestream, and nitrogen removal with no Sidestream. In other words, the dewatering stream will be returned to the mainstream. The difference here between these two cases yields up $400,000 savings you saw in the previous slide. So the benefits then of Sidestream treatment are about a 10 to 20% reduced tankage for the mainstream activated sludge system, about a 10 to 20% reduction in aeration demand, as we saw in the previous slide, about a 25 to 100% reduction in demand for supplemental carbon, about a 10% reduced solids production, and a source of AOBs that will be returned to the mainstream and supplement the nitrifying population in the mainstream activated sludge mixed liquor form of bioaugmentation. So let's look at the pilot investigation. So the goals then were to minimize the risk. You got to remember that, well, maybe most of you are not aware, but we started down this road about 6 years ago, and at that time The process had not been implemented in North America. In fact, most people didn't know about it. And at that time, there was a huge concern that because of the very slow growth of the Anammox bacteria and the difficulty in enrichment, that there was significant risk to the viability of the biological process. And also, centric quality does vary a lot from plant to plant. So the county decided that it would be appropriate to utilize, or rather to take on a pilot demonstration for their specific circumstances. So we defined design criteria for, at least performance criteria, for the pilot facility of 85% ammonia removal, 8% TAN removal, and overall 75% TAN removal. And we also defined a process stability goal. We're looking at a sustained 30-day minimum period of achieving these performance goals. As a simple sketch of the pilot plant, our centrate was being fed to a storage tank above ground, and then the feed pump would provide 750 gallons per day into the pilot system at a volume of 1,600 gallons, and then discharge the effluent tank. In practice, this is what it looked like. It came in this trailer, or this box trailer, and it was laying on its side. So when it's righted, you can see that the total height of this reactor is about 14 feet, although the actual side water depth is about 10.5 feet or so. These are the blowers sitting outside the facility. And then up on the top, you see a close-up of the hydrocyclone and the mixer. And then looking down inside the reactor, you'll see the stand here for the online instrumentation and the mixer, and the sort of reddish color representing the typical red color of the Anammox bacteria. And this is just a picture of the schematic that's shown the HMI in terms of what's going on inside the reactor. So those of you familiar with an SBR would recognize this as a typical sequence of fill, aerate, settle, and decanting. But just to walk you through this process, shown here is the depth difference between the starting point at filling the reactor and the final point. And the filling process actually occurs, although it occurs in a defined period, it consists of a number of subcycles where we go through an aeration step for 10 minutes, a 10-gallon addition over just under a minute, mixing, and so that the total subcycle time will be 16 minutes. And the reason for doing this is just to provide the control for the pH, because you're adding alkalinity and consuming alkalinity, and this allows the controller to maintain fairly tight control if you're adding small amounts of the dewatering stream in this manner. So once you fill the reactor up to the designated level, there's a final period of 20 minutes of final aeration, 16 minutes allowed for settling. You might say 16 minutes doesn't sound very much, but remember, these are granules. They settle like rocks. They very, very rapidly settle to the bottom. And then there's a period for decanting, and then there's a little time built in before the next cycle starts. So previously you saw a picture taken from above here, but this is where we had the online instrumentation. At the time, we really didn't know what it was we should be monitoring closely, so we maybe erred on the excessive side. We monitored flow, dissolved oxygen concentration, pH, ammonia nitrate level, and temperature, as well as the flow rate. As we'll see later on, there were really only 4 criteria that we really needed to monitor, and while it was nice to know of these things, it wasn't necessary. On a daily basis, we grab samples of the influent, effluent, and reactor mixed liquor to measure ammonia, alkalinity, suspended solids concentration. Similarly, in the effluent, but we also monitored for pH and nitrate. And in the reactor, we also monitored nitrite, and I'll explain why in a moment. We also spent some of the time looking at methods of trying to assess the viability of the Anammox bacteria. And there were a couple of methods that have been developed by Bernard Wett, who was the original inventor of this technology. And simplistically, one of them is to measure the activity of the AOBs, the ammonia oxidizing bacteria, by taking 2-liter samples, aerating and mixing them, having added ammonia to the sample, and then monitoring the decline in ammonia and the increase in nitrite and nitrate. Here you see a couple of folks involved in the pilot demonstration. Lynn Williams from Brown Caldwell, and Amanda Summers, who's the PM for this activity from the county. And the parallel test was to actually evaluate the activity of the Anammox. So having added nitrite to a sample of mixed liquor, and these samples were mixed, and you can see the 2-liter vessels were covered so as to avoid any air intrusion, and then to measure the change in ammonia, nitrite, and nitrate levels, as you see here in the graph. The ultimate objective then was to measure the activity in terms of the milligrams of nitrogen removed per gram of TSS per hour. And over the course of the test, you'll see there's a gradual trend in the activity of the Anammox in the reactor. The test is not as sensitive as we'd have liked. You can see the spread of data, so you can, if you take lots of measurements, then you can get a good trend. And so we decided that we should take a look at some other methods that the operators could use on a daily basis. And the reason for all of these is that we can't use the mixed liquor volatile suspended solid as an indirect measure of activity of the activated sludge. And because the Anammox bacteria is are only one component of the mixed liquor, somehow you have to try and get to looking at the granules. One of the ways we started testing was to resurrect the old spin test that was typically used for monitoring mixed liquor solids and by many operators. You centrifuge down the sample, and you'll see here there's 2 layers of sludge, slightly different colors. You can see the red organisms below, and then above here are the heterotrophs that we don't need to grow in the system. And it's this upper layer which is removed by passing the mixed liquor through a hydrocyclone, and the density difference between this layer and that layer is large enough for the hydrocyclone to get rid of this upper layer of sludge and retain the red organisms, which is what we need to retain. A very simple method, easily done, very simple operational tool. The other one that could be done is to take a very small sample, something like 60 microliters, put them on a grid, put them under the microscope, and then count the number of these red granules that you can see within a given area. So these two methods were pretty simple, very quickly done, and provided us with a much better feedback than the more complex Anammox activity experiments that you saw earlier on. So some results. This gives you, if you like, the whole ball of wax over the whole course of the study. You see the timeline across the bottom, 3 sets of graphs. This is a specific nitrogen loading rate expressed in a mass of nitrogen per volume per day. And then this shows the removal efficiency for nitrogen and TAN. And lastly, the reactor nitrite concentration. So you can see here the loading varied quite a lot, and there were all sorts of things that occurred during the course of the pilot, which unfortunately I don't have the time to go through, but there were everything from power failures to stalled mixers to overloading conditions to simple operational issues that happen on a day-to-day basis, which caused us to modify our loading rate. And it took quite a while to get up to the sort of target levels. But the important thing is that if you look over the whole course of the study, we were able to hit a targeted 85% ammonia removal for most of the period, and it was relatively stable over this long period. We actually developed a different method of measuring stability, as we discovered that nitrite was probably the most sensitive characteristic to monitor. Nitrite would cause some inhibition, so as you'll see in a moment, we monitored that all the way through the study, and the target was to keep it below 10 milligrams per liter. So if you summarize...
This is Jenny. I was just going to say you're fading a little bit, so if you could speak up or face the phone microphone a little more, please.
Sure, is that better?
Yes.
Okay. So we see here, these were our targeted input characteristics, and this ended up being what we actually saw. Our ammonia load was pretty close to what we expected. What we didn't anticipate is the wide range in alkalinity, which actually ended up being a slow climb through the whole test period, which had some consequences. Our feed TSS was pretty high, and because we had that storage tank ahead of the pilot, we were able to settle out a lot of the solids. And our achieved goal was, our target goal was 85%. We got to 82% or so. You'll see how we got to almost 100% in the last stages of the test, and our TIN removal exceeded our goal. So the other thing is, despite these numerous interruptions and a toxicity event I'll show you in a moment, the system just kept trucking along at this kind of performance level. So my interpretation of this is that these organisms are very, very robust. You can beat them over the head with a 2x4, and they seem to be just totally immune to a lot of difficult operating conditions. So was it a success? Well, you saw the performance data. Our belief, and everybody who was associated with the test was convinced that these are pretty robust organisms. This process was time-based control, and the only critical measurements we needed to make were pH and DO. I'll talk about this in a moment. The staff had the opportunity to gain familiarity with the process, and we developed a couple of simpler methods to measure the Anammox bacteria than would have been available prior to this point. So a couple of points to note. Centrate solids concentration was pretty high, and this is related to the way in which the county managed its solids dewatering system. And so fortunately we were able to settle a lot of the solids out, but it meant that we had to design for sludge removal as a pre-treatment step. Inline probes, some of them were not reliable. We thought it was related to the turbidity, but in any case, the data were not critical. These are the three items that we found to be critical. The reason for nitrite, if you look at this chart, you'll see the loading rate. We were advised to start at this high loading rate, which is a design condition, and immediately the nitrite level escalated and caused an inhibition. So we reduced the loading rate temporarily, and contrary to what's in the literature, the nitrite just disappeared, then came back up, and within 2 or 3 days, we were back up to a reasonable level of performance. And the take-home message here was that nitrite are not toxic, as the literature indicates, but they're inhibitory and they're reversible. The Anammox bacteria recover very quickly, but at the same time, it's important to track these nitrite concentrations so you don't get into this kind of situation that we did. Alkalinity, our expectation based on all the European installations was that the process would operate around pH 7. As it turned out, if you look at the data collected here, the pH drifted down and to pretty low levels. It finally stabilized at about 6.7 or so. And it turns out that the influent alkalinity and dewatering streams, if you look at the European installations, tend to have a higher level of alkalinity. And so they were not prepared for us having to add alkalinity. And just for the sheer heck of it, at the end of the trial, before we had to give up the pilot, we just threw in half a bag of alkalinity, and the system just responded immediately, and we were able to achieve almost 100% ammonia removal. So the question then becomes is, okay, is this really economically viable? Yes, we can dial in whatever removal rate we want by adding alkalinity. When we did the math, it turns out that this is not an economic option for us to pursue. So a few details of the design. We ended up retrofitting an existing aeration basin that was going to be abandoned. There are 5 components: settling basin to take out the solids, an equalization basin. The county wanted redundancy, so we provided 2 reactors in parallel, and an effluent storage basin. The operation was based on 7 days a week operation, but in the early days of the plant, it's probably going to be less than this. So the equalization tanks are going to be helpful in that transition period. These are the kinds of criteria that we designed the plant for in terms of gallons per day. We collected a lot more centrate data, so we have more confidence in this being a better number to design around. And based on our experience, our design load is going to be, our peak design load is going to be this value. And then the average loading rate is 0.6 kilos of nitrogen per cubic meter per day.
Henrik, this is Jenny. It's time check, 5 minutes.
I'm almost done. So the system then, the settling basin is going to operate at a constant level. Actually, why don't I just flip to this? This is a three-dimensional view of the existing aeration basin, which is being retrofitted to accommodate the Demon process. You'll see here one portion of the tank is going to be set aside for centrate settling. This portion is set aside for the centrate equalization. And then we've got two reactors, this one here and over here, and between the two there's effluent storage from which it's returned to the mainstream process. So going back to the details, the equalization basin can provide up to 1 day of hydraulic retention time. It will operate on a variable level. And the two reactors with a 6 to 8 hour cycle time will operate in an alternating sort of fill and draw basis. And then the decant will pass through a hydrocyclone to the effluent storage tank. The tank itself, the storage tank, is a variable level facility with ability to constantly pump the effluent to the mainstream and periodically take out sludge using the hydrocyclones if the settleability is not as good as expected. The county was concerned about reliability and redundancies, which is why we have two Animox reactors. We can transfer sludge from one reactor to the other using the cyclones. We can operate with one reactor out of service. And there is the ability that in the worst case scenario, the mainstream process will have the ability to take the full side stream flow if necessary. And then lastly, we've got redundancy with the two process train in terms of the pumps, the hydrocyclones, and probes and blowers. And this is just a close-up of the inside of the reactor, showing the feed pumps to the cyclones for enrichment, where there's basically just a continuous movement of the mixed liquor and discharging of the unwanted heterotrophic denitrifying bacteria. And you see here the decanting mechanism and the other set of cyclones, which are used for extracting the final treated effluent. There's another side shot of the decanter with the low and high positions. And then I'll be happy to take any questions at this point. I must add the startup of the system is going to be next year. You see here the folks who are engaged in the pilot activity: Adam Klein, Lynn Williams, Kate Green, Dave Newman from Brown & Caldwell, and this is Dr. Bernard Wett, the inventor of the process, who came to work with us for a week or so during the pilot study. Jennifer, I'm done.
Thank you very much. Perfect timing. So I invite you to submit questions through the panel. We do have one for you, Henrik. Do you believe the excess nitrate was removed by denitritation?
The excess nitrite or nitrate?
Nitrite.
Yeah. Well, it's removed by the Animox bacteria, but the as I illustrated earlier on in the talk, but stoichiometrically about 11% of the ammonia will be converted into nitrate the nitrite should be taken out completely by the Animox. The only reason that nitrite begins to show up in excess is if you overload the system and the Animox activity starts to be inhibited, and that's why we monitor the nitrite to make sure that never occurs. I don't know if I'm answering the person's question, but that's my understanding of the question.
Okay. Thank you.
We have two other questions. One is, what's the cost per pound of nitrogen removed for this system?
Oh, you got me.
I think that actually was for the carb system, that question.
There was one for the carb and one for the Demon.
Off the top of my head, I can't remember, but I can certainly provide that. I just don't know the answer to that right now.
Yeah, and this is John Fraser. Let me add to that. That's kind of a hard and misleading number, I think, to make generalization about, because I think both of these systems are going to be driven by existing infrastructure, what can be modified, what can be avoided, and that dramatically impacts the cost. And there's two components to the cost. There's the capital cost component that is almost case-by-case site-specific based on what you're able to reuse and the configuration. And then there's the operating costs. And the operating cost is also site-specific and might be dependent on the degree of carbon limitation your wastewater has for denitrification and or phosphorus removal. Certainly the Animox, speaking about the Animox, will provide a benefit related to carbon, so that may pencil out from an operational cost favorable if you have to supplement, another system with carbon. And then the same thing a little bit with power costs. The Animox process will require less power for aeration. But, then it's kind of a matter of opinion of which one has the overall lowest operator time and component replacement costs. So I would say a generic answer probably doesn't do that question justice, and it probably needs to be evaluated on a case-by-case basis. And both systems have certain advantages and disadvantages depending on the conditions at a certain site.
Yeah, I would agree with everything that's just been said. I guess it gives me the opening to illustrate why the county elected to go this way, because they were going to abandon the old aeration tanks, and we pointed out that, hey, there was a free concrete tank sitting here that we could retrofit for this process, which saved a lot of money. The plant was, the influent wastewater was carbon limited to a great degree, and that gave us an opening here to save money again. And so overall, on a life cycle cost analysis, we showed that over a 20-year period we could save the county $6 million and make this a much less costly exercise compared to treating everything in the mainstream. So John's quite right. I think everybody, if they need to, if they want to consider Sidestream treatment, they really need to do very close site-specific analysis and take into account all of these things that we've discussed, the alkalinity, the carbon, the availability of equipment to retrofit, and the overall ammonia loading that's represented by in the Sidestream, as well as the final effluent ammonia concentration. As we're finding out in other installations, folks who are looking for effluent ammonia concentrations of much less than 1 milligram per liter will definitely try to take advantage of this kind of technology.
All right, I think we're out of time, but I wanted to give a big thank you to Dr. Henrik Melser of Brown and Caldwell, and also Steve Walker and John Fraser of Carollo for sharing their knowledge with us today. We can send out and will send out answers to the remaining questions after the webinar. And I just wanted to remind everyone to stay tuned for the third webinar in the Sidestream treatment series, which will be announced once we lock in the speaker and the date. Have a wonderful afternoon, and Michael, over to you.
Thank you, Jennifer. This is Michael Rainey in the PNCWA office. I'd like to echo Jennifer's thanks to everyone involved. As you leave the webinar, you will be asked to fill out a very brief evaluation. We'd appreciate your input on that. Within 1 hour, you will receive a link to request CEUs. And PDFs will be available within 24 hours. I'll send you a link for those. And last but not least, a recording is planned to be available on the PNCWA YouTube channel. Thank you very much. Thank you, Emerging Technologies Committee. Rick, thank you very much.